Hey kids, time to do implicit differentiation, right? Which is really just part of the chain rule, right? Remember in Calc 1 when I told you to take the derivative of this expression with x's and y's because you couldn't get y explicitly in terms of x, right? And you would say, all right, well, that's 3x squared plus, and then you assume that y is a function in terms of x. So you would say 3 times that x stuff squared times the derivative of that x stuff with respect to x. And then you'd use the product rule over here. The first function times the derivative of that x stuff plus y times the derivative of 6x. And then I would say, hey, can you get dy dx by itself? And you would move all the dy dx stuff over to one side and then factor. And then you would divide. And notice you had a derivative rule, but with both x's and y's in it. And that was the price to pay for x's and y's being, right, all mixed up together. So I want to look at this a little bit differently. I want to get all the x's and y's onto one side and a constant on the other. And I want you to think of this whole left side as a function in terms of two variable, and it's equal to a constant. And then I want to think of taking the derivative of both sides. So I'm going to get, taking a derivative of any constant is going to give me 0 on the right side. But taking a derivative of f in terms of two variables, we could think about our tree, where y depends upon x. X is independent, y depends upon x, right? So how do I do that? If I want dy dx, right, where f is kind of, right, f is my dependent variable, and my dependent variable is y, because we're saying y is a function of x. So right, what do I do? Partial f, partial x. Technically, if you want to think about the fact that x is dependent upon itself, right, it's an independent, so you're multiplying times dx over dx if you really want. I just kind of usually stop my tree here if I'm not dependent upon anything else. And del f del y times dy dx. Now remember, I am just in terms of one variable, so I don't have to use my partials. Can you get dy dx by itself now? This is a 1, so it's negative del f over del x divided by del f del y. Well, that's kind of crazy. So let me formalize this a little bit. And I want you to keep both of those boxes in mind. As long as we have differentiability all over the place, if we differentiate both sides of an equation with respect to x, we get 0, right? Because the derivative of 0 is 0. There's what my tree diagram just showed. And then we isolated dy dx, and we got this formula, right? The last here is just a little bit cleaner version. Kind of uncomfortable, right? When I'm doing a derivative, anything with derivatives and x is on top, right? Because I always think derivatives slope y on top. But here, I have to remember both the negative and the fact that x is on top. So let's take that same problem and let's use our Calc 3 partial derivative knowledge on this. Step 1 get all the x's and y's onto one side and a constant on the other. Step 2, I want to find dy dx. So remember, it's like this is my f. My f is like my y, right? Right? It's dependent. So del f del x. Step 3, del f del y. Step 4, use the formula. Hey, look at that box that you had before in your notes, right? Now, it doesn't look exactly the same. That's because the negative has been applied up here, right? Isn't this the same thing as the opposite of negative 6y and the opposite of positive 3x squared? OMG. Kind of crazy, right? Now, I'm not going to go through all this for a bunch of problems that you could do with your Calc 1 knowledge. Right? We're going to make this a little bit more complicated. Instead of having 2 variables, we're going to have 3. So let's pretend that I have the unit sphere. So I want you to think of the left side is all my variables mixed up together, and I want to take the derivative of both sides. So taking the derivative of a constant is going to give me 0. And then I'm going to use my tree. F is in terms of x, y, and z. Now we have 3 variables. We're going to choose one to be the dependent one. I'm going to choose z to be dependent, right? So these are my 2 independent ones, so I can kind of stop there. But z, we're going to say, is holding the place for a function in terms of both x and y. So how would I find the derivatives, right? What if I want to find the derivatives with respect to x? Now remember, this is the same thing as saying z, right? Which is a little weird because z is, but we did that exact same thing before. So we're going to say, well, technically times dx over dx. Right? And what if I want it in terms of y? Technically times dy over dy. Right? And each side is equal to 0 because you're taking the derivative of a constant. Now, I want dz dx by itself. Sorry, del z del x by itself. Yes? How about here? Right? Since my f is z, you can replace all your f's with z's. Crazy. So formally, if z is equal to a function in 3 variables, we call that function capital F, set it equal to 0 or any any constant really, and then take the derivative of both sides. I should write C. If I want dz dx, that's what I get. And if I want del z del y, that's what I get. So let's try that one with our unit sphere. So our formulas were, I want to find and remembering my formulas, so here, what do I have? Right, 2x over del f dz. Don't forget to negate. Oops. Negate df partial f partial y. And hopefully that makes sense with what our sphere looks like, right? Our unit sphere. Cool, huh? We'll do some more examples and more complicated examples together in our live session. And I will see you then.